Hello, kids. Let's do section 13.2. 13.2 is going to be split into a couple of days, though. So this is just going to be day 1 of section 13.2. And look, there's some more calculus, right? We finished the last section with limits, right? Which was, if you think about single variable calculus, one of the first things we did, right? And then we moved to derivatives. So notice that a derivative of a vector function is defined in much the same way. It's a limit, right? It's a limit of slope of the secants. So if you want to look at this picture here, right, it's very similar, right? I have a secant vector between 2 points on the curve between the vector r of t and then r with time, the original time, plus a little bit, right? H is a little bit, very close to 0. And then that moves me to another point on my space curve. So here is your secant vector. Well, the tangent vector is, as you shrink this delta x to 0, right, this line Q slides back along our space curve here. And this is our tangent vector, r prime of t. No, you are not going to have to do the formal definition of derivatives in vector land in 3D space. You're going to be allowed to just, you need to understand that where it comes from, but no, you do not ever have to do the formal definition of derivatives. Right, so here's a bunch of verbiage, blah, 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 blah. I'm not going to read it to you. And I expect you to take, when you're taking notes, that these are things that you do have to know. Notice that I need to make sure that the derivative does not equal 0 and think about why that might be. And that what the tangent line is, right, the line through a point that is parallel to the tangent vector. Right, so I have a tangent line and a tangent vector, right? Two different things. And then, of course, I have the unit tangent vector, which is r prime over, I don't know why that apostrophe is so far down there. But the tangent vector divided by the magnitude of the tangent vector. So this is a cool little, right? Look at that space curve there, kind of, right? Kind of misshapen infinity sign almost. And this purple vector right here is the tangent vector to the space curve at that point. So this applet will show you how it kind of moves around, which is kind of cool. Right? So you can see as time passes, there's the unit vector moving along that space curve. I'm sorry, there's the tangent vector moving along that space curve. Right? And you can see how it kind of stays on the outside of the curve, right? Thinking about the concavity, where you would draw a tangent line, right? It's on the outside of the curvature or of the concavity. So what if I ask you if r is defined this way, right, as a function, an x function, a y function, and an h function, which of course I can write in IJK format too, right? I call this component form, and this I call IJK form. I don't know if that's appropriate or not, but that's what I say. And assuming that f, g, and h are differentiable. Then the derivative, right, the derivative of that vector valued function is just the derivative of the separate functions, written in either form, component form or IJK form. And then there's some rules, and these derivative rules should look very familiar to you. Right? They're very simple to single variable calculus. Right? The derivative of a sum is the sum of the derivatives. The derivative of a constant times a function is the constant times the vector valued function. Look at this. The derivative of a function times a vector, right? That's a little bit different. We don't have that in normal and. A function times a vector is the derivative of the function times the vector plus the vector times the derivative of the vector function. That should sound familiar to you. But look at 4 and 5, right? 4 is the derivative of a dot product. And 5 is the derivative of the cross product. Be careful. Cross product is not commutative. Be very, very careful with that, right? You can't have the derivative of u cross v is not the same as the derivative of v cross w. And then here's the chain rule in vector value world. Now, notice that there is no division, right? We don't really do division of vectors, right? It's just not a thing. So example 1, let's take this function r as vector valued function, and let's find r prime of t, right? So you took single variable calculus for a reason, and you paid attention. So r prime of t is just the derivative of cosine 3t. What is the derivative of cosine? It's sine, right? Is it sine or is it negative sine, though? Excellent. It is negative, but don't forget to spit out the derivative of the inside. Well, that's easy. And the derivative of sine is cosine, but spit out the derivative of the middle. Done and done. There it is in IJK format. And here's that curve, right? If you notice, this is the curve cosine 3t, sine 3t, and t. And this is just, they define t to go from -5 to 5, right? But that is our r of t. And there is the tangent vector. You just found the equation of the tangent vector at any t. And this applet shows if I stopped it at some point and said, oh, at t equals 2, what is the tangent vector, right? I would just plug in 2 into my r prime at 2, and it would stop that tangent somewhere. Oh, I didn't want to stop it there. I wanted to stop it at 2. Right, so there, if I plugged in, I would get that tangent vector. So look at this. I want to take the second derivative. Well, the second derivative is just the derivative of the first derivative. So notice I already got r prime, right? We just got r prime already. So what is our double prime? NBD. Or in component form. Good. Find the tangent vector and the unit tangent vector to this curve. So if you want to pause the video for a minute and see if you get what I get. And then come back and see if we're at the same place. So what do you think I need after this? There's the tangent vector. Now I need the unit tangent vector. So that's the unit tangent vector is r prime of t, what? Divided by the magnitude of r prime of t. So what is that going to be? I can drop the negative, right? Are you okay with that? I'm going to be squaring, so who cares if I have a negative? Now check this out, though. Hey, right? What's that going to be? That's going to be 4 cosine squared plus 4 sine squared. So I'm going to factor out the 4 from that sum and get sine squared t plus cosine squared t. Hey, hey. Don't break my heart and tell me that's 2t plus t, right? I mean 2t plus 4. I mean 2t plus 2, right? You wouldn't break my heart and say any of those things, right? There's nothing to be done there. I mean, I guess I could factor out the 4 and make them a 2 there, right? And I could probably factor the 2 out of there and cancel some stuff and make it a little bit simpler. But I'm okay. What if I wanted you to write the vector equation of the tangent at a particular point? Let me erase this stuff to get it out of the way. What would you do there? Write the vector equation of the tangent at a particular point. What do you think I need to do? Well, there's a couple things, right? I need a vector equation, right? So how do you write the equation? The equation needs, vector equation needs a point and a slope, right? So here's the point I want. I need to go back to the original, right? And plug pi over 3 into there. Sine of pi over 3 is root 3 over 2, right? Times 2 is going to be root 3. And then cosine of pi over 3 is a half, times 2 is 1. But then I also need the slope at pi over 3. Now I erased my r prime, but you have it in your notes, right? So it's 2 times t. So that's 2 pi over 3. And then 2 cosine, right? 2 cosine of pi over 3, but cosine of pi over 3 is 1/2 times 2. So that's just going to be 1, right? And then 2 sine pi over 3. Negative, though, we had. So negative root 3. So there is my point and my slope. So I'm going to put my point here. And my slope here. Oh, snap. All right, so that is all that we're going to do for the video. And then I'm going to make sure that we do some examples together live in our next session together on Tuesday. See you then.